solution to the equation. And the first thing is the optical theorem. All of you handed your exam in, right? So you don't have to copy it. You hand in a late exam and say, oh.
I went to hospital like the last 2 days because I have a serious stomach.
Oh, you haven't handed in your.
So I'll leave. Yeah.
Okay, maybe you can leave. So, I haven't graded the exam yet. I looked at a few solutions. I think most of you took your solution from Jackson, and some of you took from somewhere else. Adita told me he found a nice solution from Sang, Kong, and Shin. And I just told me that he found a nice solution in Panofsky and Philip. I saw your solution too. Where did you get yours from? It's quite nice.
It was like Jackson, but I changed it a little bit.
Oh, from Jackson as well. Okay. So Jackson used some very unconventional notations. He wrote Huygens principle in quite a different fashion. So I just want to elaborate on that. That you can write Huygens principle using different notations. And why do you have that? Like you can usually write Huygens principle using this notation. I omega mu G R prime according to my book. This was n cross H R prime. And then you would have something like curl cross G R prime. And then maybe n cross E or something like that, according to what I have in my book. And this would be dr prime, dr prime. And then maybe there's a minus sign here. But then if you look at Jackson, his notation looks quite different. So let's elaborate as to why that's the case. And of course, G, according to what I have in my book, is this function over here. E to the I, K. Okay, so if you take the code, you only get the first term. So the second term simplifies to something very simple. This is, if I call this the scalar Green's function. It simplifies just to the scalar Green's function. The first term actually can be written in terms of two terms. It could be written as a scalar Green's function, and then times n cross H, should be n prime between. And then there's a del del term. Del del term actually gives rise to a term that looks something like this, Br. And if you move on to the del del term inside, then you will have something that looks like this, G R prime. Okay, you will have something that looks like that. Okay, the del del term has two terms. One can be left outside the integral and moved inside. And then you have this term which simplifies to something like, since this annihilate each other, you can simplify this to look like something like grad G cross n cross grad G, that's right. So the second term simplifies to that. Of course, you can do things that makes this operate on something like that, or this becomes a del prime. This term can be written in terms of charges. Okay, this is essentially divergence of J. Okay, and then this can be I omega sigma. Okay, and this can become a surface charge. It becomes a surface charge, then you can write this term in terms of n dot E. Is what Jackson did. Okay, there's an n dot E term in Jackson. Okay, so it's actually just this formula written in a different fashion. And oftentimes you see Huygens principle written in this very confounding form. involves that. And you also find that Stratton Chu will look something like this. There's a very old formula due to Stratton and Chu. Okay, Julius Stratton was the president of MIT at one time. He wrote this electromagnetic theory book in the 1940s. Lanjin Chu was a professor at MIT before my time. Okay, so it's not my Chu. Okay, it's different. Okay, he's also quite famous. So when you look at Stratton Chu formula, it also has something like this. Okay, and then so what is the gist of the optical theorem? I think the gist of the optical theorem is this. In my opinion, I haven't seen it written in any textbook, but I think this is what happens. So everybody starts with the total field, I mean the incident field plus the scattered field. The H total is incident plus scattered. And then if you have any scatterer, you have an incident coming in, then you can calculate the energy that's been absorbed inside, okay, by, as everybody did, integrating over a surface S and then calling this absorption, okay, with a minus sign, because N is, say, if you're pointing outward, then negative, this corresponds to energy that's going inward. And then when you substitute that in, you get 4 terms. You get minus WA is 4 terms. There should be a real part of this as well. Okay, there should be a real part of this somewhere. Okay, so if you substitute that in, you will have EI cross HI conjugate, it's 1 term. And then you will have EI cross HS conjugate plus ES cross HI conjugate plus ES cross HS conjugate. And then you have these 4 terms. And then ES. And as all the textbooks say, this term must integrate to 0 on a closed surface, because if it's the incident field, there's no loss. So if you have only the incident field, this must go to 0, and this must be the scattered energy. Okay, this must be the scattered energy, and hence, if you put this to, if you call this part W prime, then it says that minus W prime is WA plus WS. Okay, so you just need to evaluate W prime. It will give you the energy absorbed by the scatterer as well as energy scattered off by the scatterer. Okay, so why is it that finally, if you look at the answer, it depends only on forward scattering and nothing else? The energy absorbed. The extinction cross-section, which is the energy absorbed plus the energy scattered. Absorbed means that you might have some lossy material in here. Okay, the energy can get absorbed inside. And then scattered means that the energy gets scattered. Why is it only dependent on forward scattering? I think the reason for that is due to a concept called power orthogonality. Okay, you might have seen this in waveguide theory before. That is, if I have a waveguide, if I have an arbitrary shaped waveguide, if I write the total field inside the waveguide as sums of modes of the waveguide, and then the H field as also the sum of the modes of the corresponding waveguide. Then if I look at the total power, E cross H conjugate, integrated over the cross-section of the waveguide, okay? So this might be n dot z ds. And then if you substitute in, you will have summations of two terms. And then you have some cross terms. Those cross terms always evaluate to 0. That is called power orthogonality. So finally, instead of a double sum, when you plug in here, you only have one sum. Okay, you only have one sum then. Seems that modes do not interact with each other. And these modes do not interact with each other because they have different k vectors. Some modes will propagate like this, some modes will propagate like this, some modes will propagate like this. Okay, what it says is that if the k vectors of the plane wave are not the same as each other, they will not interact with each other. So what it says is that of these terms, and if you look at this term over here, okay, this scattered wave gives rise to two vectors that are all pointing in all different directions. But there's one where the scattered wave k vector aligns with that of its incident field. Okay, only that part of the scattered field is important. That is, energy can transfer from the incident field to the scattered field only through that interaction. The interaction where these two are phase matched. It's almost like the concept of phase matching. If you want to transfer energy from the incident field to the scattered field, they have to be phase matched. So in the scattered field, pointing in the forward scattering direction, would there only be energy transfer? So if you know the forward scattering cross-section of, if you know the scattering amplitude of the object in the forward direction, you know how much energy has been transferred from the incident field to the scattered field. I think it's due to power orthogonality. I did not prove it, but I think it's due to that concept. If you work out this and substitute a plane wave in the far field, a plane wave coming in, I'm sure that those will evaluate to 0. Okay? Other than the fact that, except when they're aligned with each other. When they're aligned with each other, their phases cancel each other. You get a constant tone. If they're not aligned with each other, you integrate over the surface, it should be 0. Okay, I think that is the gist of the physics behind the optical theorem. Okay, I don't think any textbook says that, but I think that's the reason. Okay. So, what about the antenna aperture? I think RCS everybody knows, right? RCS everybody knows. Cody, do you know RCS now?
Yeah.
You know what it means, right? Except that there was you think when you have 20, was it 20 dBm? What does it mean? What does it mean, 20 dBm? Is it 10 meter or 100 meter? 100 square. What?
100.
Should be 100? I think it depends on how you define the. I think it depends on how you define the dBm, right? The standard notation is that if it's power, you use 20 log that number. If it's not power, it's 10 log that number.
No,
Is it the other way around?
No.
If it's power,
when it's power, we use 10.
okay. dBSM is 20 log or something. So this is not area 1 over area 2. Okay, so since this is not power, then you put 20, am I right? And if this is power, you put 10 out there. So if this measures to be what? What was the answer? 20 dBSM? A1 over A2. So this is like 1, right? Log of A1 over A2 is equal to 1. Am I right? So this must be A1 over A2 must be 10. Am I right? A1 over A2 must be 10, and this is 1. A1 must be 10 square meters. Am I right? I think some people say 100 square meters. Right? It's wrong, right? Did I reason it right? I don't do this all the time, so. So this is not in terms of power, so you put 20 out there. It's how DBSM is calculated. Is this how you calculate it?
No, I think they do 10 longer.
You put the 10 here?
Yeah.
Just so the scattering cross section has unit of area, so it cannot be it shouldn't be the fraction of two areas. Right.
No, this is normalized with respect more to 1 square meter. So it should be an area ratio of 2 areas. But since this is not power,
I think
so you should put 20 out there, right?
it is kind of like a power because like DVSM is the area that is intercepted of power. So if
So you should put a 10 here?
yeah, because you could just as easily multiply the incident powers
Okay.
on top of each other.
Let's say we put 10 here, and then you should have 10 here. Then if that is the case, then this should be a 2, and it should be 100. 100 square. Okay. So I guess it depends on whether you put a 10 or a 20. Okay, it looks reasonable. I can think of this as A1 times P incident. A1 times P incident. So this has to, this is in terms of watts per meter square. This would be in terms of watts. So this can be ratio of 2 powers. So I should put the 10 here. Then the power can cancel. And then, okay, then it would be 100 square meters then. It's a huge object. Huge object, right? 100 square meters is 10 by 10. 10 by 10 is about 30 feet by 30 feet. It's a huge object.
I don't think that area is actually the physical area, it's the area that.
The area that it appears to be,
Yeah.
appears to have intercepted the energy.
I think it also has to do with how fast it might be traveling, or if it's like, for an example, like they said an aircraft carrier, not an aircraft, I'm sorry, like just fighter jet is 100 meters squared, but a car is also 100 meters squared, so I don't know how.
The car is 100 meters
Yeah.
square.
When I looked online, I looked for like, they had like tables for.
Okay, that looks very big to me. 30, can a car be 30 feet long? Yeah, that looks like something very
But
big.
I think physically, maybe like the way reflections happen.
Okay. It looks very big to me anyhow. 100 square meters. Okay. So that is the radar cross-section part. What about the antenna aperture part? It's equal to lambda squared over 4 pi g. Why does this formula look so ridiculous when lambda goes to infinity? Effective aperture of the antenna becomes very, very large. And some antenna engineers will say that, wow, you should lower the frequency so that you get a larger aperture. But what's wrong with this formula? Why doesn't it work out that way as you think? If you look at the derivation, this derivation of this formula is predicated on the fact that you have a perfectly matched system. Okay, so the power received is the effective aperture times power incident. So you make this assumption and you assume that the system, you have an antenna, you have an impedance of the antenna coming in, and then you have it matched. Maybe it will generate a voltage source. You can model the voltage source generated there, and then you have this perfectly matched system. In order for the received power to be maximum, and the inductive part will cancel each other, then the antenna impedance will have a radiation resistance plus this part over here. Okay. This part becomes larger and larger as the antenna gets smaller and smaller. Just look at the Hertzian dipole. The Hertzian dipole looks almost like a capacitor. So when the wave coming in, it looks like a capacitor, and this part is going to be very large, but it's a very poor radiator as the frequency lowers. So this part is going to be very, very small. Radiation resistance actually, I actually worked out that radiation resistance somewhere. Radiation resistance of an antenna is extremely small. Anyhow, I do not have it, but this thing is proportional to omega squared, okay? Because it has to be proportional to the acceleration of the current, so it's proportional to omega squared, or omega form, I don't remember now. But it gets exceedingly small when you go to the long wavelength limit. So you have a system where it's almost impossible to match yourself to the radiation resistance. You have copper losses, other kinds of losses, dielectric losses, and all kinds of losses will start to predominate. And then you have that, you have to add in some kind of antenna loss, dielectric loss, something. You can never match this system perfectly to get it to work. So the gain of the antenna drops. The gain of the antenna would drop, and then the effective aperture would saturate as you go to lower frequencies. And you will never have an infinitely large aperture as you go to lower frequencies. Does this make sense? It makes sense, right? Yes?
So how if we insert impedance matching circuit and use impedance transformer, so we can still match it.
Impedance transformer,
Yeah.
like what? Like an inductor?
Like
What? Like a step waveguide, or like a quarter wave transformer?
like something. I remember it's a copper wire wired on a ferrite core.
Yeah, but those will introduce losses, right? So like a Hertzian dipole is roughly a capacitor. Hertzian dipole has a lot of electric field around it. When you go to low frequency, it's a capacitor. Of course, the natural way that if a wave comes in, it induces a voltage source, you add in a voltage source here. Then you try to transfer this to a load. And in order to cancel this capacitor, you can add an inductor. You can have a load, right? You get this to cancel each other, which is what you're thinking about, using a Faraday coil or an inductor to cancel this one. But this has loss, so you have to add in some loss here due to this one. And this one is going to get very, very small. Okay? And no matter what you do in terms of matching, the loss is going to dominate over this radiation resistance. And hence, you're going to get very little energy going to your load. And hence, you can never transfer energy properly. You have dielectric loss, you have ferrite loss, you have all these things, and all the tricks you have in antenna engineering cannot save you.
Does a quarter wave transformer have losses?
Quarter wave transformer is a transmission line concept, right? Transmission line concept, you also introduce dielectric losses. You can never make a quarter wave transformer. You can do that in air. Air has the least amount of losses. But if you start making microstrip lines, you have dielectric losses, you have copper losses, and those are going to dominate over the rest of the design. Okay, so you can never find this. Did anybody find a generalized derivation of this formula in any textbook? Which textbook has it? Who?
Yeah, cross has it.
Process.
Krauss has it? Oh, okay. Krauss has it. Okay. So most of the textbooks I look up just show the Hertzian dipole version. Okay. So this would be a good qualifying exam problem for you. Okay, so you may get asked by some professors, like myself, when you give you the phone, ask you why. Okay. The others are, well, Hermitian properties, and then what else is interesting? Slice projection theorem. And then how do you get a nanoparticle to change its resonance frequency? That concept I think you should know. A nanoparticle, the resonance frequencies can be derived using long wavelength concept. So you make the wavelengths very large compared to the size of the particle. Then shape, the size becomes unimportant. Size becomes unimportant in the long wavelength length. A particle of this size, if it's much smaller than wavelength, will have the same resonance frequency as a particle of this size. Right? So shape is not important. No, not shape. Size is not important anymore. However, shape is important. So if you change the shape of this particle, it's going to change its resonance frequency because you kind of alter the kinetic inductance and the capacitance in the structure. Okay, so you can change the resonance frequency by altering its shape, but not its size, because Laplace equation is scale invariant. Of course, if you go to larger sizes where wavelength effect becomes important, the resonance frequency will get affected. But then if you were to sweep the frequency, would you observe other resonances? Why? I see you nodding your head. So
that's because partly it's due to free electrons, where the Drude models, like, and then after a while, it's due to boundary electrons.
no, I don't think that is the reason. I think that the reason is that we have this formula, right? I think it looks something like that. When we solve the sphere problem, we are only assuming a dipole. Dipole incident field. The incident field is ZE in or something like this. You only excite the dipole response from the sphere, and it has this very simple thing. But I never found anything written up explicitly in any textbooks, but if you excite the sphere with multipoles, you will have a multipole response. And then this formula will look something, I don't know how it gets changed, but maybe L plus 1. I think it's written in some research paper somewhere. The denominator will get changed due to different multipoles you are considering. And then the resonance frequencies of those different multipole orders will be different. So you sweep the frequency, you will hit different resonances because you hit different multipole responses. Okay? I found at least one research paper talking about that. I couldn't find any textbook that talks about that. Okay?
What do you mean?
Yes?
What do you mean by exciting them with higher order multiple? How can you do that?
Because this problem, we assume that the incident field, the potential incident is Z, E naught or something like this, right? And this corresponds to something like this. This is entirely a dipole field. And if you translate this in terms of spherical harmonic, maybe it's P1 cosine of theta or something. This translates to R cosine theta. Okay? But I can change my incident field to be PL cosine theta. Different multipole order coming in. I will excite a different response. Okay? And then the dipole, this is a dipole response, the multipole response will be different. And then the numerator and the denominator will be different. And then if you look at the denominator now, the resonance frequency has shifted. And if you sweep the frequency, you should be able to see this response. Dipole, quadrupole, octupole, in general multipole. At least I found one paper saying that, okay? I couldn't find any textbook that says that. Yes.
In the given nodes, the nodes talks about the bonded electrons. So that's transformation of energy.
Oh, you mean the magnets?
Yeah,
electron
the electron node senators.
Okay, you talked about that.
Yeah, you'll see like different resonance because of
Okay.
the
Because
bonded.
different energy shells will
Yeah.
have.
The charger. Okay, I can take a look at that too. Yeah. I can take a look at that. Maybe give you some credit.
Does a plane wave have when we expect a plane wave in terms of spherical harmonics, does it have L greater than 1 component?
Not this one. This one only has this one.
Okay.
Okay, but if you have higher order term, it will excite the other terms. But plane wave has very little quadrupole or octopole components. In the long wave filament, those octopole, quadrupole, and high order multipoles are of higher order. Actually, they vanish completely when omega goes to 0. But that doesn't prevent me from saying, I have this sphere over here, I put a very small dipole over there. And both of them are in the long wave filament. This will produce all multipoles. They can excite this thing. And then you should be able to see the other resonances. Okay, I think that's all I want to say, right? I think that's all I want to say. And of course, the last problem, kinetic energy of the cold plasma, you can find in many textbooks as well, if you know where to look. Aditya, did you find it in any textbook?
Herman House, right?
Herman House has it. Yeah, I actually talked about it last semester, right? In the waveguide theory course. So you know how to do the last problem as well. Okay, that's all.